Log on, tune in, find out. Another good idea from Cambridge.
From Schlumberger Cambridge Research up the road.
Thank you, Bill. Yes, good afternoon, everyone. This is a picture of our research center, which is located just half a mile from here, west of here, along Madingley Road. Let's see if I can get this to work. Of course, it doesn't work. It's not hooked up. There we go. So, I'm going to start with a brief overview of the kind of imaging problem that the industry is facing today. The evolution of imaging techniques has been driven by a need to image increasingly complex targets, because most easy targets to explore have been explored at this point in time. And this evolution has been enabled, of course, by the phenomenal increase in compute power which is ongoing. But one of the points I want to make is that imaging is not only about computational algorithms. As we have started to use more and more sophisticated algorithms for imaging and inversion, we have become increasingly aware of the limitations in the data that we record. And these limitations boil down to three different areas. One has to do with illumination of the subsurface. The second one about the frequency bandwidth of the data that we record, in particular the lack of the low frequency components of the data. And by low frequencies I mean, let's say, below 5 Hertz or so. And the third aspect has to do with spatial sampling. So we tend to be aliased in the seismic data that we record, both on the receiver and the source side. So I'm going to talk about some of the things that are happening right now that address these three fundamental areas. And this is a very active topic for research and development in many companies in the industry. The second part of my presentation will be about the next generation imaging and inversion algorithms. And in particular, I talk about elastic full waveform inversion a little bit. So these are techniques that are now starting to make use of much more of the data recorded. Not so many years ago, a very small portion of the data recorded was actually used to produce images. But we're now seeing much more where we're starting to use a majority of the data that we record, not only first arrivals or certain windows in the data only. So you know what's happening there is that we're starting to use more and more physics that is correct for the wave propagation and can turn much of that noise into useful signal. So this is what I'm going to be talking about, marine seismics mostly. What you're seeing here is a schematic picture of a marine seismic array. It's overlain over the city of Oslo, so you get some idea of scale here. And the reason why it's city of Oslo is because that's where my company build our seismic acquisition systems. But what we're talking about is a boat up here which moves with about 5 knots. It tows 2 sources here that fires every 10 to 15 seconds, emitting energy that reflects from the subsurface and comes back to the surface of the Earth. And it's recorded using hydrophones. And these hydrophones are located along streamers. Each streamer can be 10 kilometers long, and we can tow 8, 10, 12, 16 streamers or so in the water. So we're talking here, the hydrophones are spaced 3 meters apart, so we're talking about tenths of thousands of channels live recording data at 2 milliseconds or 4 millisecond sampling rates. Yeah, so one of the points I'm going to mention here is, you know, we call this 3D marine seismic, but it's clearly not the perfect 3D experiment. We have a bias in the recording array here, and we make some approximations or force ourselves to live with some limitation in the data. One particular thing here is that these are spaced 150 meters apart, and you actually start alias data at very low frequencies there. So there are some things that we need to work on still. So this is actually 10 years old technology now, but what we do as well is that we are able to steer and position these streamers in the water very accurately. So we can go back to predetermined positions, and we have these birds that allow you to position them both vertically and horizontally. So you just saw the bird flip here into depth steering mode from a vertical steering mode. So this has proven to be really useful, and I'll actually show you an example later on of where we use this steering to acquire data that is much better fit for complex imaging. But originally this was actually developed for time-lapse applications where we want to go back and conduct a repeat survey to image fluids as they move within the reservoir. So you need very high precision and you need very quiet streamers in order to do that. So as I said, much of industry is really concerned with complex imaging, and in particular it often involves salt. So salt in many areas of the world is buried very deep below the sediments. It has a low density, so it tends to be released from these salt structures and raise up through the sediments. And you tend to get very rough surfaces. Salt is also fast, so you get a sharp velocity contrast between salt and sediments. And the hydrocarbons is then trapped either below the salt or at the salt flanks. So this is, a very complex imaging problem for all those reasons. And this is actually a picture of a real salt body or a model of a real salt body in the Gulf of Mexico. You can see the scale up here. So you can get very complex salt bodies that you need to image and image beneath. This is another movie here. So this is a movie over a model called the BP salt model, which BP released in 2004 to benchmark different imaging algorithms against each other. So it's based on geology from the Gulf of Mexico. In this finite difference simulation, it's 2D and it's acoustic, but still you see a very complex wavefield that starts to evolve. So you have a source that goes off up here. We have a seismic streamer located here, and you can see if we say we're interested in imaging the salt flank over here, we are going to need fairly sophisticated algorithms that just don't rely on some kind of first arrival assumption only. We're going to need to make use of all of that part of the wavefield that you see propagate through the model. And if you go elastic here, you'll see mode conversions and things that between P and S waves that complicates things substantially. Okay, so let's move on to talk about these three fundamental limitations. So the first one has to do with illumination. So imagine if you want to shoot a seismic survey over this salt body. If you go in this direction back and forth, or if you go in that direction back and forth, you clearly will get a very different image. And that's what I'm talking about when I talk about illumination. We need to essentially illuminate this salt body from all kinds of different directions at the same time. So that's why industry some almost 10 years ago started to look at what's called wide azimuth acquisition. So again, BP was one of the first companies to do this, and you're now employing one or two or more vessels shooting at the same time. So you see one vessel here, towing the sources here. Here you see the fronts of the streamers. So now the different boats can shoot into the spreads of each other, and you can create all these wave paths that you wouldn't record if you only had one vessel out. There are many different ways that you can do this, to sort of evaluate how efficient they will be, one can create a rose plot like this, where you have azimuth here and offset here. So here you have the conventional narrow azimuth survey. Here we have a few different other combinations that start to involve many vessels shooting in all kinds of different directions, and this quickly gets very expensive and to fill the circles over here like this. So one of the things that I'll give you some examples from my company, because that's what I have all the slides about, of course. But here's a different way of doing this. So I showed you the steering capability that we had before, and the fact that you can develop algorithms that can provide very quiet streamers while steering. So somebody suggested, why don't we steer all the time here and go around in circles like this? with the center of, well, the circle is slightly shifted, but always over this point. So you will get a very nice distribution of offsets and azimuths in the point in the middle here. And you can do it with one vessel, for instance. So that turns out to work very well. So it's called coil shooting. And you have here just a marketing slide that shows how you can get a very nice distribution illuminating a target. So what you saw on the last slide was actually a navigation plot of a real survey like that. So this is the kind of ideas, novel developments that's happening. I think the practice for recording seismic data is very, very different now compared to 10 years ago. That's really the point I want to drive home. The second area has to do with the lack of the bandwidth, and in particular the lack of low frequencies. So the fundamental problem here is that, you know, when you set off a source, emit energy that reflects from a target, it propagates up, it's recorded by the hydrophones, but it doesn't stop there. It is reflected downwards with a -1 reflection coefficient, which creates a destructive constructive interference pattern in the data, which is known as ghosts. So I'll just illustrate here with a simple finite difference simulation where you will see a plane wave coming vertically from below. It has a leading edge that is white here. It then reflects down and it becomes a leading edge that is black. And that gives you these notches in the data where you lose certain frequency bands depending on how deep your streamer is located. So at the bottom here, I have another movie that shows what happens as we lower the streamers. So on the horizontal axis, I have the frequency response. On the vertical axis, the amplitude. The blue curve here is the pressure data, the hydrophone data. And as we're now at 3 meters depth, we start to lower this. We're now down to 6.5 meters, which is a conventional towing depth. You can see that we lose all the frequencies down here, and we start to lose frequencies up here. So that's a price we have to pay if we are interested in this full bandwidth over here. But it's not satisfactory, and in particular, in lots of areas, we need to have better low frequency recordings over here. So the red curve here is the solution that you would like to do. That is namely to record particle velocities in the streamer as well. Now, that turns out to be extremely noisy because hydrophones are acceleration cancelling, whereas a hydrophone picks up, whereas an accelerometer picks up all the noise modes in the streamer. So there have recently been some attempts to try to do this, and I think it's coming. But at this point in time, we're struggling very much with, or the industry as such is struggling with controlling the noise here. So one can do other things. One can say, okay, I don't care about these high frequencies. It's the low frequencies I'm interested in. So that's been a number of successful stories there from Shell, Satyr Singh at IPGP have worked on this, and various other groups. You can also say, right, if I would like to have the whole bandwidth, I need to have streamers at different depths. And that's another way of going about things. So here I show another example of what we can do. So here we're looking at 2 layers of streamers. We have a layer of streamers. This is like a cross-line view, right? So we're towing 8 streamers behind the survey. And the shallow streamers are towed at a conventional depth, let's say 6-7 meters. And they capture nicely along the red curve here, the intermediate to high frequencies. Then we put the occasional deep streamer. And the purpose of that is that we get the low frequency ghost response. It's quieter to tow deeper. And because we're only interested in the low frequencies, we don't have to put them as densely. And then we can merge these 2 data sets together to get a broadband data set. So that's a way of getting around this problem with the noisy accelerometers. But it's clearly not optimally cost effective. I have some data examples here that shows how this works in practice. This is an individual shot gather for a conventional data, and this is for this combined data set. And you can probably visually just see here that it's less noisy, and you just have much more character of the low frequencies in the data. And this can then be also processed through to final image, of course, and this is when you see the better results for the combined data set. And finally, just a slide here to show you that I'm just not showing pretty pictures that you could artificially manipulate, but actually when you feed this into an inversion algorithm, which has been done here, you get a much better result with these broadband data. And that's illustrated on the right, where we have inverted for acoustic impedance using a conventional versus one of these combined data sets. Okay, the third and final topic of these acquisition issues has to do with spatial sampling. So I mentioned here that these are spaced 150 meters apart. So that means that you start to alias data already at 5 hertz. And you saw previously I said we're interested in maybe 100 hertz or more sometimes. So this is a serious problem in the cross-line direction. And the same thing on the source side. These operations are very expensive, they're cost-driven, so you need to tow these streamers as fast as possible. So you have to compromise on the spacing between shots as well. So here is a concept that we developed a few years ago. So let's say now that we can record the vertical particle velocity in the streamer together with the horizontal components. So the question is, what are we going to use the horizontal components for? So you get a clue from that by looking at the equation of motion, where the gradient of the pressure is proportional to the time derivative of the particle velocity. So, in other words, if you have the horizontal particle velocities, you get access to the spatial gradient of the data, which you can then should tell you something about the spatial structure of the wavefield away from the recording location. So, this is a simple illustration of what this is about. Imagine that this is a plane wave in space coming from the side in the cross-line direction. Imagine you have 4 different streamers recording the wavefield. If you have the pressure only, you know the amplitude. If you have one of these 4 component streamers, you know the amplitude and its derivative. So if you sample the data this sparsely, which is aliased, and you try to reconstruct this waveform, the single channel interpolation, this is one of the solutions. Whereas with this multi-channel reconstruction, you know that the solution above is not the solution, and it picks up on this one. This is just a very simple example of the idea. Of course, there are many solutions that could fit this particular example, but turns out that you can look at there is an equivalent sampling theorem for multi-channel data called the multi-channel sampling theorem, which is an equivalent of Shannon's sampling theorem, which tells you that how densely do I need to sample my data if I have access to the measurement and its gradients. So that's what I'm illustrating here. This is wave number frequency space, and because we're located in water, we know that we cannot have any energy that propagates faster than the speed of slower than the speed of water. We can see apparent arrivals that come at infinite velocity, but not at slower velocities than 1500 meters per second. So that's partition up the FK space into this cone and this white part, and all energy will be located in here. If I now discretize this, I have, let's say, an infinite number of equally spaced sampling points, spaced 50 meters apart, 75 meters, and 100 meters apart. I start to introduce aliasing, and that's illustrated by this diamond-shaped pattern here. If I have access to the data itself only, I can reconstruct data in the dark blue gradient. If I have access to the data and its gradient, I can also reconstruct the data in these lighter blue diamonds. You can actually take this even further because you have more information than that. We have the ghost that I talked about. We know where the sea surface is, and that constrains the problem even further. So potentially this type of information can be extremely valuable by several, I'm not going to say exactly how much valuable it can be, because it's obviously something that will depend on how noisy your data is and so on. But factor 2 or 4 is certainly possible, I think. So here is just quickly an illustration of some tests we have done with this. So this is now a state-of-the-art model that's used in industry now called the SEAM model. Complex salt again. There's actually the logo of SCG below the salt. So Bill Symes was one of the people who were heavily involved in generating and benchmarking these data from these synthetics. So we have used these data, and we have here a shot gather for a geometry that looks like this. We then subsample this to conventional streamer spacing. Actually, I'm pretty generous, I suppose, but in some sense it's conventional. 125 meters apart, and you can see here that we have a heavily aliased data set. These are complex geology, and it's hard to see exactly what direction different events are dipping in, and to not get any cycle skipping here. So we're looking at the pressure, cross-line component, and vertical component of particle velocity. So all these three data sets now go into the reconstruction algorithm, and we get an output that looks like this. We have the original reference data here, and we have the difference to the right. So this is the kind of results that we are quite pleased with, to get be able to reconstruct data that is so heavily aliased to that degree of accuracy. So that is what I was going to say about the acquisition part of the talk here. So let's move on now to say talk a little bit about imaging and inversion. So I've used the term imaging here a few times, and that's something we talk a lot about in oil industry, and it's what exactly do we mean by that? So I'll try to describe that through a flow chart here. So the options that you have for imaging can be illustrated in this way. The first thing we need to do is to answer the question whether velocity separates from reflectivity. So that's not necessarily an easy question. Traditionally, that's what we have done pretty much exclusively up until 10, 12 years ago or so. And the reasons for that is that the Earth, in many places of the Earth, tends to look something like a slowly varying background with sudden interfaces or sharp velocity impedance contrasts that occur. And when we do a seismic experiment with a source up here and receiver located like this, we get arrivals that are governed by this background velocity, which is refractions. And in particular, the low frequencies will be governed by that. And if you look at far offsets, these are dominating. So these then will tell you about the kinematics, the velocity of the background. Then we have these type of events, which are reflections, which occur at nearer offsets and typically for the higher frequencies more. So given that we know the kinematics and have the velocity model, we can just measure the arrival times of these reflections, and we can position them accurately in space. So that's the workflow that we used for many years. So the first question then we need then a model estimation, and that can be done in many ways. This kind of diving wave tomography, for instance. Imaging itself then consists of downward continuing the recorded data and some kind of estimate of the source wave field into the Earth, followed by some kind of correlation of the two wave fields, which is what we call an imaging condition. And depending on how you do that downward continuation, you use Green's functions that are based on ray theory or the full wave equation. We talk about ray-based methods or wave equation-based methods. And these ray-based methods was really the main workhorse in the 80s and 90s. And then increasingly over the last 10 years or so, we've seen these wave equation methods becoming much more popular because they are much more suited for these complex imaging scenarios I talked about.
So what's RTM?
Reverse time migration. So you can think of reverse time migration as, the movie I showed originally over the BP salt model. You run that backwards in time for the received wave field, forward in time for the source wave field, and correlate the two wave fields. So you can then start to think about that's a really nice framework to use that long wave train of all the different arrivals in principle, provided that you have a good velocity model, etc., etc. So the other option is that we take a full waveform inversion approach. We don't pretend that velocity separates from reflectivity, and that can then be used both for getting the structure of the subsurface, but also to invert for rock properties or in the subsurface. So what is full waveform inversion? The goal is to find the Earth model that can explain the recorded data with a full wave equation. And mathematically, that's you have a cost function with the difference between data and recorded data and model data, which you then minimize. So this was techniques and theory developed by many people in the 80s and 90s, in particular Tarantola in the 80s did a lot of work on it. But nobody really did anything with this, and there were two reasons for that. Computers weren't fast enough, and actually these complex problems weren't the places where people looked for hydrocarbons necessarily, with the lower oil price and so on. Then in 2004, Gerhard Pratt showed a talk at the EAGE, a conference here in Europe for oil and gas seismic applications. And I think this really took a lot of the industry by surprise, how these methods could come up with such good models in a very complex geology. And since then, there has been quite a bit of a race between different oil companies and oilfield service companies to develop this technology. And obviously, lots of the research groups around the world are heavily working on this and contributing in this area as well. A bit about the cost. You can here see some rough cost estimates. This is a slide I've got from Dave Nichols, some of you probably know. So these are just ballpark numbers of what the cost is. But if you say a 3D typical Kirchhoff pre-stack depth migration cost 1, reverse time migration cost 100, and that's paid off. Reverse time migration is what you need to use in many parts of the world now. Acoustic full waveform inversion, another order of magnitude more expensive, getting to be very expensive. But for the last 3, 4, 5 years, people have presented these types of results at conferences. Still though limiting the frequencies that they can do these computations for. It gets more and more expensive the higher frequencies you want to go to. Elastic full waveform inversion, another 2 orders of magnitude up there. Very challenging, and I think we need a serious breakthrough in the methodology before we can do that. But I'll show you an example why it makes sense on why we want to go there. So what is elastic full waveform inversion? Well, the goal is the same. We want to explain the recorded data but this time with the elastic wave equation. The opportunities is the physics is better explained by the elastic wave equation. We can get P wave amplitudes that are better than if you use the acoustic wave equation. And isotropy in the subsurface is an elastic feature. The shear waves, and we also have surface waves that you can't propagate in an acoustic solution. So you can see that this boils down to 2 things: amplitudes and turning what otherwise you have to think about as noise into useful signal. The challenges of this are the same as for acoustic full waveform inversion, but you have a forward problem that is much more expensive, because you got to model shear waves, which you see up here with very fine small wavelength, at the same time as you model the longer wavelengths, P waves. And you also have a much larger null space. In principle, there are 21 elastic parameters, so you need to decide on what you actually want to invert for. The applications are for reservoir characterization to get rock and fluid properties, structural imaging. Even if you're only interested in the structure, for these complex scenarios, you can have certain waves that bounce off salt flanks that you just need the elastic wave equation to just get right. And the last example here is land surface data, which I haven't showed anything about, which is like 90% noise if you think acoustically. But all of this is, a lot of it is you need the elastic wave equation to describe. So I think if I want to have a breakthrough on land, you need to maybe image the near surface first so that you can back off that distorting lens that it has on the reflections that you're really interested in from deeper. So a synthetic model. So this is a gain from the C model. You're seeing a small chunk of it only, so not the whole model. So this is work that I got from a colleague at SCR, James Rickett. And what he has done here is he shows the p velocity, the s velocity, and the density. And just to show you that this is a difficult problem, this specific model is difficult, we have here plotted, you can basically there are empirical relations where you can say in many areas of the world, if I have a p velocity of a certain number, I put an s velocity to one-to-one mapping in between them. And one of those models is called the Mudrock line. This model doesn't follow the Mudrock line, and you have a lot of structure here in shear velocity that you will never be able to recover from a simple acoustic full waveform inversion with some empirical relationship. So that's going to be our benchmark. Can we retrieve these subtle deviations from the Mudrock line? This is the raw data. These data are up to 30 Hertz. We have 4 different shot gathers here. We do some pre-processing of those data. So that's band pass filtering and some muting. And these are now the data that we're going to invert for. And the one thing I want you to note here is that these data, a lot of people are focused on using the refractions only in the inversion. But here we're actually using refractions and reflections. So we're using everything from near offsets to far offsets. Yeah, somebody's gonna, what we've done here is that we actually use finite differences in the inversion as well. So, but I'm going to argue that this is not, this is a mild form of an inverse crime because we have, we're using very different scales in the synthetics. So in the finite difference code, the implicit boundary conditions will be very different. So we're looking at lower frequencies, the actual synthetic data we generated on a much finer scale using higher frequency content. So this is our final result using an acoustic full waveform inversion algorithm. So I can flick back and forth between those two for those 4 shot gathers, and you see that it gets a lot of the rivals fairly well. The kinematics at least looks good. This is now the elastic result. I go back between elastic and acoustic, and there are certainly some differences here. And finally, I compare the elastic to the original data, and there are some differences, but there are definitely some improvements. These are the final results now plotted. True model on the top, VP, the inversion result at the bottom. And here we have the VS in terms of deviation from the Mudrock line. On the top is the true model, on the bottom is the inversion result. Let me just first point to some of the things that we're quite happy with. All those green arrows identify features that the inversion algorithm did pick up on. But we do have 1 or 2 things which are not there. This particular event or feature is actually invisible on a towed streamer data set, or largely invisible. It belongs in the null space for the offsets we looked at. So that's something that we will have to continuously to struggle with, and I think that really ties back to one of the main points that I wanted to make, how important it is to have an acquisition system that can record the data that you need. So this is very similar to the kind of data in the North Sea. 15 years ago there was a reservoir that was discovered using seabed seismic data called ALBA, which you couldn't see on towed marine data, but it was visible once you recorded the shear waves in the sea bottom. So maybe for some areas you might need to go to record seabed seismic data to pick up on these features. So I mentioned that this is extremely costly. So what areas could help to provide the breakthrough for elastic full wave inversion? So a lot of effort is going to looking at new computer architectures, and a breakthrough in the modeling kernel would certainly be very important. And there's also research in the inversion algorithm, exploiting the data better. So, in this example I showed you, we took the entire shot gather, but it's certainly true that some parts of the data do contribute more than other parts of the data. So can you be selective there in focusing your effort in certain areas? And finally, the problem parameterization. Being clever about how to transform your data or parameterize the problem is a key aspect. Which brings me to some conclusions. So there has been some major advances in imaging and inversion over the last 5 years, and I think it's safe to say that 3D acoustic reverse time migration and full waveform inversion are here to stay. They have revealed limitations in the data that we record, and the need for better physics in the inversion. So I showed you one example, a simple example, but where elastic full waveform inversion enables a better data fit than acoustic full waveform inversion. And in some cases we are able to recover the shear information. But the null space means that fitting the data is not always, or is not enough by itself. So we're going to need to use additional information and constraints. The fundamental problems of non-uniqueness and cost remain, so these are certainly very important areas for research for the future. So I have a number of colleagues I need to acknowledge who have contributed to this. Chris Chapman, James Hobro is sitting here, Ed Craw, Dirk-Jan van Manen, Nick Moldovano, Dave Nichols, Ali Osbeck, James Rickett and Max Vassallo. And again, this is a picture of our place half a mile that direction. Thank you.
Before we take questions, I should have mentioned that Johan is Director of Geophysical Research in SCR.
That's right, thank you.
Yeah, a quick question on one of the very late slides where you had this feature that you said would be in the null space of the data you measured. So it suggests that if you want to make an inference for that, you should check if it's there. I mean, so is there a methodology where people interpreting these pictures can say, well, is that in the null space? If I'm going to make a decision based on it, can you put it back in and see whether the picture without that feature would also be consistent with the data?
Yes, I would say yes. People are very likely doing that on a routinely basis. Basically, how much confidence can you have in a certain result? I think that's key. There are some people from the oil companies who will be able to answer that more than I perhaps, but I don't know if you want to add anything to that question. No. I think so. That's absolutely true. Uncertainty is a huge problem here.
That's what Christoph Stork used to call driving around in the null space.
Yeah, that's true. Thanks.
Following on from your last remark there, I don't know whether you were here yesterday, but Dean Oliver from Bergen gave a talk yesterday where he was extolling the great virtues of the ensemble Kalman filter, because it would appear that it can deal with the non-uniqueness problem and with producing a more efficient data and inversion problem, algorithm that can take into account all sources of uncertainty. So I wonder, is that one of the breakthroughs that perhaps the industry should be looking at, and has it done so already? Because it's making great inroads in production history matching and in weather forecasting, which are very similar problems.
Right. So yeah, no, I wasn't here yesterday actually, but these are the kind of directions that we definitely need to look at. We have several groups in Schlumberger, as you know, who work on these problems, but there are that is certainly one of the major directions.
Just I was thinking, you were saying about Albert Tarantola's work, because he was ignored for many years. And what we're seeing here with the ensemble Kalman filter is really putting the icing on the cake, because it's really finishing off what he started all those years ago.
Yeah.
Questions?
I know that you are working in the geophysical seismic group, but after all, when you make decisions in the oil industry, you're not doing that on velocities. You're doing that on the prospect of petroleum, hydrocarbons, and water and other things. So there are inverse problems besides this that are crucial for using seismic data in decision making.
Yeah.
Can you make a few comments about that?
I would prefer you direct these questions actually to some of the colleagues in oil companies here who are more working on integrating different problems like that. But
with a better velocity model, you can then, if that translates into an improved image, and there's one, you get a better structural image as a result if the velocities are improved. If that also gives you better attributes that you can extract from that image, that's when we start to go into the world of inverting those attributes to meaningful rock properties.
I do think there is a lot of mileage in identifying features and structures here that this data contains a lot of organized information that we're not using fully at all.
Rock physics, these kind of models has caught a lot of interest.
Yeah.
You mentioned a way to try to improve the aliasing. I think the picture you show was mainly geared to acoustic waves.
Yeah.
And in your second part of your talk, you were mentioning the importance of going to aliastic.
Yeah.
What would be the impact if you want to try to have non-alias shear waves?
Non-alias shear waves. That would be very challenging.
Yeah, but if you want to do full waveform...
Sure. So I think you will need to do some kind of tricks to get away with that. The shear waves can be so short wavelengths. I was mostly talking about P waves here, but that's certainly a very good question.
Please keep going on.
Yeah, okay.
This is traditional.
Okay.
Meaning that we switch machines.
Very good. What I was going to say, even inline in the shear wave data that we have recorded, the data are aliased. I've seen data sample at say 25 meter spacing, and you see try to fit that with some kind of statics models that clearly are aliased. Step one will be to get finer sample data in lines and then take it from there, I think. Yeah.
This may be a very naive question, but in your list of challenges or problems toward the end, you listed the null space problem and ill-posedness separately. Is the null space problem a type of ill-posedness, or is it a completely separate issue?
I'm trying to think how I put that up now, actually. I need to think about that a little bit, maybe.
Well, by 5 o'clock, the answer will arrive.
That's right.
I was intrigued by your proposal to do multi-component marine acquisition in order to interpolate between the streamers. I think the understanding at the moment is that if you tow a geophone, then especially at low frequencies, say from 0 to 20 hertz or so, signal tends to be noisy because you're towing all the time, and how do you propose to can you comment on that?
Yeah, it's a hugely challenging problem, but I think the companies who are working on developing acquisition systems can, if you can understand the noise modes, the most noise is actually coherent. So digging deeply behind that, I think there is good mileage for getting something up.
Yet another inverse problem. Okay, with that, hold all the rest of them for 5 o'clock. We'll go ahead and thank our speaker again.